This is infinite series. Just a quick note, this is a finite series, this is an infinite series because this terminates at k, from k equals 1 to n, and this is to infinity is our sum. So here's an example. Consider a geometric series 1 plus x squared plus dot dot dot. We'll write s of n equals 1 plus x to the squared to x to the n minus 1, i.e. s of n is the sum of the first n terms, then x s of n is this when we multiply this series by x, so we get an extra term, and therefore 1 minus x multiplied by s of n equals 1 minus x to the n. Thus if x does not equal 1, s of n, we get this. So if x equals 1, s of n equals 1 plus so on and so on, plus 1 equals n. Now if 1 is greater than x, as x to the n goes to infinity, as n goes to 0, as n goes to infinity, hence s of n will go to 1 over 1 minus x as n goes to infinity. The series here of x to the n therefore converges for 1 greater than our magnitude of x, and it sums 1 over 1 minus x if x equals 1 and s of n equals n, and s of n goes to infinity as n goes to infinity. If x equals minus 1, s of n equals 1 minus 1 to the n over 2, and s of n does not tend to any limit as n goes to infinity. Now if x is greater than 1, hence our geometric series here, x to the n equals 1 over 1 minus x as n starts at 0 and goes to infinity. And we'll let a of n equals 1 over n plus 1 for all n contained within the positive integers. Then a of n equals 1 over n minus 1 over n plus 1, hence a1 equals 1 minus 1 half, and a2 equals 1 half minus 1 third, a3 equals 1 third minus 1 fourth, and so on and so on. Now a of n an minus 1 equals 1 over n minus 1 over n. Now a of n therefore equals 1 over n minus 1 over n plus 1. Thus s of n goes to 1 as n goes to infinity. This series a of n converges and equals 1. We'll let n equals 1 to infinity of a of n and n equals 1 to infinity of bnn be convergent series. We'll write s of n here and t of n in terms of our b's. Then adding these series we get this, and sn plus t of n and s plus t as n goes to infinity, where s equals n to infinity of an and bn equals t as n goes from 1 to infinity. Hence the sum of our sums, a plus b, converges, and the sums here into the n, so adding convergent series is easy, but multiplication can be more problematic. Example, a to the n equals 1 over n, where n is contained within our positive integers. Then a to the n goes to 0 as n goes to infinity. We'll let s of n equals a1 plus a2 and so on to a to the n equals 1 plus 1 half plus 1 third up to 1 over n. And we show s of n goes to infinity as n goes to infinity. So our sum a of n diverges despite a of n going to 0 as n goes to infinity. To achieve this first, let's bracket the sums given here. Now the final term in each bracket is the reciprocal of a power of 2. Now we consider the sum of the first 2 to the n terms here, which is greater or equal to all this, which equals this. Now since each bracket in the second line has sum 1 half, as each term is positive, we see s of n is an increasing sequence. Moreover, s2 to the n is greater or equal to n plus 1 over 2. So s of n is not bounded above, hence s of n goes to infinity as n goes to infinity. Thus the series of 1 over n diverges. Our example, let a of n equals 3 to the n plus 1 over 5 to the n plus 1 to the 4th power. Then dividing through again by n, we'll end up with this because we know these two diverge. So they basically blow up. More and more numbers you put in, they just blow up. And well, yeah, as n goes to infinity, they'll go to 0 effectively. So we'll end up with 3/5 to the 4th power as n goes to infinity. And our sum at n equals 1 to infinity of a n diverges because a of n goes to 0, does not go to 0 as n goes to infinity. We'll let a of n equals 1 over the square root of n. Then a of n equals 1 over square root of n is greater or equal to 1 over n for all n. We'll write s of n and t of n here, where b of n equals 1 over n and s of n is greater or equal to t of n for all n. So s of n tends to infinity as n tends to infinity because Tn goes to infinity as n goes to infinity, i.e. n equals 1 to infinity of a of n diverges. Now we'll let a of n equals, in brackets here and parentheses, 2n factorial to the 2nd power divided by 4n factorial for all n containing our positive integers. Then for a of n greater than 0, an plus 1 over an, we get this, and expanding out a little bit of factorials, we'll see that this goes to 1/16 as n goes to infinity. Since the limit is less than 1, this converges. Now a final example, a to the n equals n squared, and e to the minus n, n plus 1 for all n contain our positive integers. Then a of n goes to 0 and a to the n plus 1 over an equals n plus 1 squared over n squared equals this term here. Once we've whacked in our exponentials, then we get 1 plus 1 over n squared multiplied by e to the minus 2 n plus 1 as this goes to 0 as n goes to infinity. So this converges, and that's infinite series.